That's the thing. To do, you know, you don't have to prove anything to anyone.
I just want to spar with someone.
You don't have to trust them.
No.
I think I'm the ones that just like it. I'm going on now.
But it's sparring. Sparring isn't fallout.
Yeah, but, yeah, some immature athlete.
I'm not good like going all out.
And once they get really good, they're getting angry, and then they start going, oh, that's how you know, schoolers that do, um, like walking them. That's what happened.
Okay, but we're not high school.
Hey, what's up?
Actually, a little bit of both. My audio design. Seeing.
Okay. Sure.
So my that's the reading part. So
Okay.
which of course we're gonna extend that because they know it's basically about.
Yeah.
Not much on. That. Stop the motor, so let you chill. Separate motor. You will basically.
I see.
They're like. Screw that you just say.
Honestly, I can tell you today. That's a little bit outside my expertise. What did they use last year? Did they use like Apple?
They didn't.
Oh, okay, I see. Oh, yeah.
Like there was the.
I see. Yeah, honestly, that yeah, that's a little bit outside my. Yeah, what have you talked to Dr. Robson about it? Okay, I see.
Yeah, and then most of the time she's talking to. Monster design.
I see.
And when she talks to Rosa. Beautiful.
Okay,
Yeah.
I see.
That's
I
the
see.
most I get from her.
I see.
Unfortunately.
Oh, okay. Well, I mean, she's definitely the expert. So she does robotics. That's kind of a big thing too. So, yeah. I mean, yeah. I have loose thoughts, but then I don't want to tell you anything to lead you astray. Yeah. I would probably just talk to her.
Where all the parts are in the one file. You would know. You know. Yeah. I'm gonna ask guy. And see the one they got. It's
I don't remember.
oh, you're not a winter. Yeah.
It's just pretty good.
But you can take over people's.
You're probably good. Cause you don't need.
That's it. Yeah, sense.
Yeah.
Can definitely be on. See, it's so easy. That's all we would get is your Scott scale, but without the sharing guy. Or the,
So,
that's pretty good.
so you know who that is? That's awesome. He's in a Shikamaru sensei. The guy was here. So he's pretty strong. I wanted to.
So. Wait a second. I'll teach you the wrong entry. Yeah, listen, like you.
You know who you are, Jim. You know who you are.
If
You're
you
wrong with Chuck.
Sonati's assistant.
You know,
She's pretty weak.
you know who you are.
Can't really go. How confidence.
You know, that's.
I know, you're looking also.
She is pretty strong.
Yeah.
You know what? Yeah, you're 100.
I'm so sorry.
This 100.
It's fine, I'll go forward. Got here early and someone was. You can see the value. So I guess. So I was just like, what? Like that sounds. Yeah, what's it, you know, the 476B? It's going to do the whole lab report on that. But if because no one's working on it at all. So if no one works on it, I'm just taking off everyone's names. I'm gonna pick 2 copies. One where I'm typing everything. I'm gonna finish my section and I'm gonna leave it blank. I'm gonna copy that, paste it somewhere else, work on that.
$100 grand
I don't want to be Geo.
I'm gonna finish my. Finish my because other people are so on the spot. Once all that's done, I'll just exactly. I see that as my own. If they want to do it, they can do it. I'm gonna go to office hours and tell the professor what's going on.
Yeah.
Like, I'll finish, I'll finish. Because I'm not taking an L to get this tomorrow. And when you get more than a year. We exam is. So I get it, but.
And the syllabus.
I get it.
Well, and then.
No.
So. Develop chapter. So I have to.
But we all have intent, right?
She's like, yeah, I'm like, if you want something.
They have to, like, no, I know they're.
That's something.
If I just want to go over it, feel like, no, what, like, that's good. But I think today's on today now, we're about it.
Says today, guys, are you ready?
Oh, yeah. Yeah, because you have to do everything. Because we are so focused on the, as if you don't know it, that's why, like, yeah, the worrying.
That's why Felix just explained.
This section.
It's so.
You're sitting right, why is this so
Connected from that.
Wait, and let Logan escape too.
Damn, there goes our manager. Yeah, it was really long.
Those blues here, Bill.
I was not the president, so I was not.
Should that be $3?
I mean, you.
That's what the tech, right? All of the education, drop the formula,
At the end
I
of
think, I mean, the officer team kind of. The advisors.
Yeah.
Yeah.
That's
last year.
She just. Came back.
It's good stuff. Oh, yeah, like this.
Alright.
So.
Oh.
That girl, the.
They have my information, so they should have.
I was like,
I saw it.
Yeah.
and then they never.
Ironically, my parents were, you know, but. Or, you know, I'm like.
It just worked out.
It just worked out.
Yeah, cause I saw like the email that was sent out by, for the like Juki report, I had no idea that was.
You were the person. You've been treating me wrong, and you're like.
That's pretty cool.
Where else? I joke, I was like, I'm gonna give you a middle name, cause I'm just actually, and I'm gonna have 4 names. And if I got finished.
Let me squeeze myself in this
You
situation.
know what? They're like, and I find like, it's not, you gotta respect me bad up, just say that. Come on, they make documents really all the time.
Oh, yeah, sure.
It's like, oh, it's like gonna be like all the initials, and it's like, pretty your full name, I'm like.
Whoa. All right, it's 5:30. Let's go and get started. All right, good afternoon, everyone. How's everyone doing?
Sleepy.
Not sleepy? Yeah, I know. I feel like I'm more sleepy nowadays. Everyone have a good weekend. The sun was not blasting down on everybody. Good, yeah. We have a few days of cool weather, but I think it's gonna heat up again this weekend, but I think hopefully not to the degree that it was before. That I find myself paying attention to the weather a lot more, and I realize that it's probably because I'm getting older now that I care more about the weather than when I was young. So that's a nice thought. Okay, so today is an exciting day. So today is our second ANSYS activity. So we're a little bit behind schedule just because of the the whole thing with the license server, but by the time we do ANSYS activity 3 next week, we should be all caught up. Okay. All right, so the activity 2, I call this the bike rank analysis, and so there's a lot of firsts in this activity compared to the first activity. So compared to the first activity, we're not going to be making our own geometry. We're going to be importing that in directly. So that's kind of the standard way that you kind of use ANSYS for the most part. We're doing 3-dimensional analysis, and so that's going to be a new thing as well. And we're going to be making our own materials. So those are kind of the 3 new I would say features, I guess, of ANSYS learning. And compared to the first activity, I'm letting you kind of choose how you do a lot of the stuff, like how you do the meshing. There's some constraints I want to place on the boundary conditions, but you can also choose that as well. So this one, pun intended, there's going to be some training wheels taken off for this activity compared to the first. Okay, so some other announcements. I did grade your activity 1s. I just did that this afternoon. So just want to repeat. So all the ANSYS activities in this class, I just grade them for completion. All these activities are they're all just for your guys' benefit to learn the software and to get used to it. So I don't really grade them for correctness. It would be kind of boring because all the reports are exactly the same to a degree too. So as long as I see that you did every single part of the activity, I see that you put effort into it. There's the responses are thoughtful. The screenshots are not the same as your buddies. Then I give you full credit for this. Okay, same is going to be true for this one and the next activity and so. Okay, any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. So first thing you should do is you should start up Workbench, and so it does take a couple minutes to start. And so if you haven't opened up Workbench yet, go ahead and search that up on here and just search ANSYS Workbench and go ahead and open that up. Okay. And while you're doing that, I'm going to introduce the activity. Or actually, the other thing that you need to do as well. So if you log on to the Canvas site, and then you click on ANSYS activity 2. First of all, you'll see that the PDF is here. So the PDF has instructions. That's what I'm be going over in a second. But there's also a CAD file for you to download as well. So the file that you're going to need for the activity today is crank_assembly.x_t. So go ahead and download that file. Okay. It may look like a SolidWorks file if you download it, but it's actually the file format's called Parasolid. So it's kind of it's a more universal kind of geometry framework that's used in ANSYS. One thing that you'll notice about ANSYS is that ANSYS and SolidWorks are made by different companies, and so you can't directly import a SolidWorks part or a SolidWorks assembly into ANSYS itself. You have to save the file as a different file format. So the one that I find that kind of works most consistently is the x_t or the Parasolid file. So you can actually just go into SolidWorks and just save your assembly or save your part as a Parasolid file. Another file format that we're going to use in this class is an IGS file. So you can also save SolidWorks into an IGS as well. Or another file format that we're going to use a lot in this class is a step file of STP. Okay. So if you ever want to import a part from SolidWorks into ANSYS and do the analysis in ANSYS, you first need to convert the file into one of those three formats. So you either need to convert it to Parasolid, which is x_t. You either need to convert it to IGS, which is either ig.igs or IGES, or step file, which is STP or STEP. Okay. So just a little bit of trivia, just in case you wanted to use ANSYS for your Okay, so go ahead and download the assembly, crank assembly. Go ahead and open up Workbench, and let's talk about the activity itself. Okay, so for this activity, we are going to be doing a finite element analysis of a bike crank. So if you don't know what a bike crank is, the bike crank is the part that kind of connects to the pedal, right? And so it connects to the pedal, and then it connects to the primary kind of gear mechanism in the bike itself, right? So it's subjected to a fair amount of loads, and so it's subjected from the weight of the person kind of weighing down on it. When the person pushes down, that's going to exert some weight as well, and of course there's going to be some reaction forces from the bike itself, as you're kind of pedaling. Okay. And so kind of the little story that I have with this activity is that you work for a bike manufacturer or bike design company, and you're designing a new bike crank to go with your newest model. Okay. So what your boss is interested in is that let's say that the design team has come up with this design for a bike crank, right? What your boss is interested in is if we were to subject this bike crank to a pretty typical load that a bike crank would normally experience, would it fail? Okay. So we're going to be doing stress analysis on this bike crank. More specifically, we're going to be doing failure analysis, right? So based on the results of our ANSYS simulation, we're going to find out whether this bike crank is going to fail or not. All right, so the material for this bike crank that we're going to be using is aluminum 6061 T6. And so the material properties for that is that the aluminum has a Young's modulus of 1 × 10⁷ psi, has a Poisson's ratio of 0.33. Okay. And we'll go from there. All right, so does everyone have ANSYS Workbench open? Everyone have the part downloaded from Canvas? Okay, so let's go ahead and get started then. So let's go ahead and open up ANSYS Workbench. Okay. Let's start in the same way that we did last time. So let's take static structural. Let's click and drag that into the project schematic here. Okay. And so by doing so, you're created kind of a static structural analysis. And we're going to be working from here. All right, so first thing we're going to do, let's import our geometry. And so if you remember from ANSYS activity 1, what we did at this point was we created our own kind of design mod or geometry. But what we're going to do in this case is that we're going to import it instead. Okay. So to import a geometry, you would right click on geometry under static structural. So that's going to open up this menu here. You're going to go down to the option for import geometry. And then you're going to click on Browse. So after you click on browse, it's gonna open up a file explorer window, and then what you're gonna do is you're gonna navigate to the place where you downloaded that Crank assembly. And so if you're using the lab computers here, most likely it's gonna be in the downloads folder. Okay. And so you can go ahead and double click on Crank assembly, or you can click on open after you clicked it, either one's fine. And then if all goes well, then the geometry will successfully import, and you should see a kind of a green check mark next to the geometry. And if you notice, the symbol changed as well, and so this is just to let you know that the file format that you imported geometry in was a parasolid file. Okay. Any questions on this? Was everyone able to import the geometry? Okay, good. So we don't need to modify the geometry at all in this case, and so we're just going to jump straight into mechanical. So we don't need to open up design mod or. Okay. But actually, before we jump into mechanical and before we start meshing, let's add our custom material property. So we skipped over this in activity 1. So we didn't add any material properties because we were just using the default material. But let's see how to add a new material. So to add a new material to ANSYS, by default, ANSYS only comes with just one material, which is a structural steel. And so if your part is made of a material besides structural steel, you need to add it in manually inside Workbench here. Okay, so to do that, we're going to double click on engineering data here. And so after double clicking that, it's going to open up a new menu that looks like this. Okay, so there's kind of a lot going on here. So let's kind of look at each kind of menu here. So the first thing that should kind of draw your attention is kind of this middle area right here. So this middle area, this lists all of the materials that you have loaded for your ANSYS simulation. Okay. So right now there's only structural steel, and so that's the only material available to us. And so we're going to add a new material starting from. If you go down to the bottom of the screen, is an outline of all the material properties for the selected material. So if you click on structural steel, this lists all the properties there for you. So structural steel, you can see, has a density of 7,850 kilograms per meter cubed. It has a tensile strength of 2.5 times 10 to the 8 Pascal, okay, and so on and so forth. The cool thing about this is that if you change the units here, so if you notice in this kind of column here, you can look at the units. If you change the units, right, the value here is automatically going to be updated based on the units that you choose. Okay, so let's say that we want to view the density in grams per centimeter cubed. And so you can see that once we change that units, then this value here is automatically updated. So it's kind of a neat thing. So if you wanted to view things, so let's say that you want to view the tensile yield strength in megapascal. So right now it's 2.5 times 10 to the 8, right? If you view it in megapascals, it becomes 250. So it's kind of a neat thing, and so ANSYS kind of goes between different units, pretty regularly. But you want to be careful with this as well, right? So right now we're only viewing this material, so we're not changing anything here. But when you add a new material, you want to be careful of what units that you have when you're adding in the value. You want to make sure that you're not adding it into the wrong units. Okay, that is the #1 mistake that happens on this activity. Is that we go in, we add aluminum, we put in the Young's modulus, but then the units are all messed up, and so you end up with a simulation that doesn't make sense, right? It happens to at least 4 to 5 people every year, and so probably going to happen to someone in class too. But just make sure that when you're adding the aluminum material properties, you're using the appropriate units. Okay, there's other things here, and so if you want to see more kind of detailed properties in terms of temperature, structural steel has that as well. We're not going to make use of all of this just because we're just using a standard kind of structural simulation. But just know that you can add a lot of other properties.
We'll see.
Any questions on this so far? Okay, all right. So let's go ahead and add our material. And so let's come back to kind of this middle section right here. Question? Yes. There's no engineering. So you don't have an engineering data here at all? Okay, I'll come back in a second. Yeah. Okay, so let's go ahead and add our material here. So let's come back to this kind of the central area. And if you notice that there is a box here for you to click to add a new material. So let's go ahead and click that. And so at this point, it's going to ask you to give a name for your material. Okay. So since we're going to be adding aluminum, so let's go ahead and name it aluminum 6061. Go ahead and hit enter. Of course, you can name this whatever you want. You know, but usually it's helpful to give your materials descriptive names. Okay, so let's go ahead and hit enter, right? And so now we've created a new material for our engineering data. Okay. All right, but what you'll notice is that there's a question mark here, right? And so this question mark, what that means is that, you know, this material is not completed. So we can't use it now, which makes sense because all we've done is we've given it a name, but we haven't assigned any of its properties at all. All right, so the next place that we're going to look is we're going to look on the left-hand side of the screen right here. And so this left-hand side of the screen, you can see that it's labeled toolbox. And so these are all of the possible properties that we can add to our new material. And there's a lot here, and there's way more than probably you know, that we're ever going to use in this class. Probably even professionally, there's a lot of features here that you wouldn't use as well. So there's hyperelastic properties, there's hyperelastic experimental data. So there's a lot here. Plasticity, creep, life, strength. We'll go over a little bit of this on Thursday when we talk about material properties, but you know, there's just know that there's a lot of features there that probably okay. Okay. But the one that we are going to use is we're going to add, we're going to assume that this aluminum is a linear material. So we're going to go to linear elastic here. We're going to open up that drop-down menu. And in particular, we're going to add properties for isotropic elasticity. Okay, so with isotropic elasticity highlighted, go ahead and double click that. Make sure that you've highlighted the aluminum 6061. And so by doing so, you'll open up this menu down here for isotropic elasticity. Okay. And so if you expand that menu down there, you'll see that there are two things that we need to specify. So there is a Young's modulus that we need to specify, as well as the Poisson's ratio. All right. Let's come back to the project specifications here. And so from the project specifications, we see that the aluminum or the aluminum that we're using here has a Young's modulus of 1 × 10⁷ psi and has a Poisson's ratio of 0.33. So let's go ahead and add these values into ANSYS. We'll start with the Young's modulus. Be careful of the units here, right? So remember the units of the Young's modulus that were given to us in the document here are in PSI. So we need to make sure that we switch the units here. Okay. So before you enter the number there, make sure you change the units to PSI. Okay. So with the units switched to PSI, let's go ahead and enter this here. And so thankfully, ANSYS actually takes in scientific notation. So you can just type 1E7. Okay. And it's going to know what to do with that. For the Poisson's ratio, we're going to enter in the value of 0.33 and hit enter. Any questions on that? Everyone able to enter those materials just fine? Okay, so the next part, so we're all done here. So from here, we can go ahead and close engineering data. So if you look at the tab up here, you can close that. And the next step is to open up ANSYS Mechanics. So open up ANSYS Mechanics, go ahead and double click on model here. Questions?
Sorry, can you go through that last part?
Yeah, so from engineering data, well, it's going to be a little bit slow. Once you've kind of finished up entering the Young's modulus and the Poisson's ratio, you can go ahead and close that tab for engineering data. So it should be kind of in the middle, kind of top left of the screen. And so you want to come back to kind of this schematic view. And then you're going to double click on model to open up ANSYS. Let me make a quick round right now, so if you're not at this point yet, you know, just raise your hand, I'll come to you, and then we'll kind of do the next part today. But if you did everything correctly, you should open up ANSYS Mechanical and you should see the part. Oh, okay, yeah.
Yeah, mine is like.
It's good, right?
All of it, and then that's.
It's very good. And then.
It's like money started. When they just landed. Sleeping.
The two. Yeah. I didn't watch that.
Oh, that was your title. Or the second, I didn't watch the second.
You guys able to get that? Okay.
Yeah, mine said that was.
Oh, that's for a feature called optimization. We're not gonna use that for this class, but sometimes if you want to optimize it through. But we're not. All right, so everyone's good? Everyone got the mechanical open? Okay, all right, so let's go ahead and continue. Okay, so once you're in mechanical, you know, you should be able to view the part as it is, right? So this is our bike crank right here. And if you open up this this tab here for geometry, you actually see that our part here is an assembly of 3 different parts, right? So we have the main body of the shaft. Okay. We have the pedal. And we have this little kind of a, you know, connecting piece that connects the pedal to the crank itself. Okay. And so if you, you know, this is very common. And so it's very common to kind of work with assemblies of parts in ANSYS. And so if you save your assembly in SolidWorks, you know, it would be imported like this. Okay. For this analysis here, you know, we're actually just focusing just on the crank itself. Okay. And so we actually don't really care what happens to the pedal or that connecting piece in between. And so what we're actually going to do, you know, before we do anything is we're going to suppress these parts. Okay. Okay. So this is something that you're going to do very commonly in ANSYS because a lot of times, you know, when you get a CAD model, you know, a lot of times, you know, when you use SolidWorks to design a part, you know, you kind of design everything. But, you know, like we talked about before, you know, whenever you're running ANSYS, you want to kind of minimize the amount of kind of extra work, kind of extra meshing space that you know doesn't really contribute much to the simulation itself. Okay. And so for this simulation here, you know, we're primarily concerned with the structure of the crank. Okay. And so, you know, we don't really need the pedal in this case. We don't really need that connecting piece. All it's going to do is just going to add extra elements for mesh. It's going to make our simulation take longer, you know, for kind of no real benefit. Okay. So when there are parts of your assembly that you don't need in your ANSYS simulation, you can suppress them and effectively just remove them from the simulation. Okay. So to suppress a part, what you're going to do is you're going to right click on the part that you want to suppress from the geometry tree. And you're going to click on the button for suppress body. Okay. So go ahead and right click on the pedal and then go click on suppress bodies. And what that's going to do is that it's going to remove it from your simulation. It hasn't been deleted, so don't worry that you didn't modify your part. So you can actually unsuppress it and bring it back. Okay. All we're doing basically is we're just removing it from the simulation, so it's not included in our mesh. It's not included in our boundary conditions. Okay, so go ahead and let's go ahead and suppress the pedal. Let's go ahead and suppress this part 9 sem2 rev so on. Yeah.
Should we have 2 materials active?
Yes. Yeah. Yeah, we're gonna do the material assignment after this. Yeah. Yeah, so go ahead and suppress those parts. The next part that we're gonna do is we're gonna assign the material. Because even though we've defined our material in the engineering data, we haven't yet assigned it to our model itself. Okay. Because what's gonna happen, in more complex cases, that you may have cases where you're simulating an assembly of different parts, and different parts of the assembly are made of different materials. Okay. And so ANSYS kind of gives you the flexibility to assign different materials to different parts. Right? And the way that you do that is from this geometry tab right here, right? And so to assign a material to a part, you would click on the part that you want to assign the material to. And then in the bottom left-hand side of the screen, you would assign the material through this drop-down menu here. So you would click on assignment. You can see right now it's assigned as structural steel, so that's kind of the default. And so we're going to change that to aluminum 6061. Okay, so that's the material that we just. So before moving forward, you want to make sure that you assign the material as aluminum 6060. Okay. Any questions on this so far? Okay. So let me go ahead and remove this. Okay, so the next step that we're going to do is the meshing. Okay, and so we had a lecture last Tuesday, about a week ago, on meshing. So now is the time that you get to kind of apply what you learned. So we're going to do the meshing a little bit differently this time. Some of you have already kind of figured this out, just kind of based on your activity 1. But ANSYS kind of gives you ways to modify the mesh using these things called mesh. I call them meshing objects. Okay, so in particular, what I want you guys to do is I want you guys to pick the size of your mesh, and I want you guys to pick the shape of the elements. Okay, so to do those things, the best way to do that, if you're going to be doing something more complex than just selecting the size of the elements, you're going to right-click on mesh, you're going to click on insert, okay, and you're going to select this option for sizing. And so what this sizing option is going to let you do is going to let you control the size of the elements in the mesh. Go ahead and click on sizing. It's going to ask you for 2 things. So it's going to ask you for the geometry where you want to specify the size. Okay. And so for the geometry, you want to make sure you select the entire bike crane. Okay. So make sure this has one body right here. And if you're having trouble selecting the entire bike crank, you can switch the mode to body selection. And so click on body selection. And so what that'll let you do is it'll let you choose the whole body of the bike crank itself. Okay. And so from there, you can choose the element size, right? So the default you can see right now is 11.255 millimeters. Okay. I'll let you guys choose that. But before we choose the size, let me show you how to choose the shape. So to choose the element shape, you're going to right-click on mesh. You're going to go to insert, okay, and you're going to choose an object called method. Okay. And so same thing. It's gonna create a new object here called automatic method. Go ahead and select on the entire body. And then from this method object, you can select the method and you can select the order. So under method right here, you can see that there's different options for the shape. So you can take tetrahedrons, hex dominant. There's some other options here, but your main decision is going to be tetrahedron of hexes. Okay, we'll talk about some of these other techniques. Once we get into more advanced meshing later on in the semester. And then for the order, remember you can choose either linear or quadratic. Okay. Okay, so I'll let you guys work for probably the next 10 minutes. And so go ahead and choose your mesh. Okay. You can play around with the sizing, play around with the shapes. And so by the end of 10 minutes, you should have a mesh that you feel kind of good. Okay. If you're kind of, if you don't really remember kind of what all of these settings do, look back on your lecture notes from a week ago. So we discussed all these things about sizing and order and shape last week. Okay, so I'll give you guys about 10 minutes to do that. And then, in the meantime, I'll walk around. So if you have questions, I'll come around and answer your questions. What's up? the size of the element. So it's default right now to something, but change to the size that your mesh looks like. Units are kind of, right now the units are used because this bike brings breeze. So I would change the unit to like centimeters. Right now that you can run the mesh, you can see what it looks like, and then you can change the mesh size. Yeah.
I bet attention.
Yes. That's fine. No, yeah, that's not a big difference. ANSYS will choose the default, kind of differently, there's a little bit of randomness to it, I mean, you're gonna change it anyway. So you can kind of choose that how it comes. Yeah. Oh, yeah. See, so there's some of the menus. I think it's really. Yeah, just for your campus. So he's gonna. I'm saving that for yes. It shows up on it. No shit. I swear. It's somewhere in the front. Yeah, it's either in the car or it's you. I have it all. Type so ANSYS does have actually have a worse case. Yeah, that's ugly. They are also trying. No, I'm not trying to force it to be X. Maybe that because you put the. Are you doing X? I'm doing 1.00. You got stuck at 5%. That's fine. I do. Wait, so there's here, but then if you want to add it. No. Text dominant. It's gonna be very. It's just, yeah, like. I think so. That's tetrahedrons. I like tetrahedrons. That's all. Thank you. That looks like me. That's what I'm gonna do. Maybe not that far. Okay. And also remember, if once you choose your settings, make sure to generate your mesh. And then you kind of see what it looks like. Okay. So don't stress about getting your mesh to look like mine. Remember, you know, there's a spectrum of meshes that work well. Okay. I mostly just want you guys to kind of play around with it a little bit to kind of see, you know, how to apply what you think about. You know, what would be kind of most appropriate for this geometry, and you know, what are kind of the most desirable mesh settings for you to use.
What is cut T?
Wait, so X dominant is the most optimal.
Yeah, so we talked last Tuesday, tetrahedrons are the most reliable for just getting a mesh, but in terms of on a per element basis, what gives you the most accuracy, hexes are.
Got it. Also, we put 0.1 millimeters.
Yep. But it's how many elements do you guys have?
No, it's stuck at 5%.
Okay. Yeah, so you want to be careful. Remember, you want to be careful about the mesh sizing. If you make it too small, then your mesh is just going to be too big, and you're probably going to run out of RAM. So, if it's taking more than 5 minutes to create the mesh, then you probably want to close ANSYS and open. Okay, everyone has to do it at least once. Everyone has to try a mesh size that's really small. Just pull up your computer and then, then you marginalize your computer. Yeah.
Oh.
This is pretty coarse, actually. No, the way you get more. I know your elements are pretty wide. So to make them smaller, you take more elements. Go to your body type. It's the size up. Yeah. So right now you're using size of. Oh, actually, you actually want to change this. You want to go to the, this is a bit. So when you're
I like my. One less.
Oh my God.
Zero point one, and then it's not showing anything. You're at.
You're using 0.1 millimeters, your computer probably crying.
Yeah, it's not solving at all. It's like.
You may want to restart again. Yeah, you want to be careful not to use a mesh size that's too small.
1 millimeter. Wait, so I'm gonna check how much it's running.
Not with the CSU budget, we don't have enough for it.
Let's do, 1 millimeter is going. We're at 505 elements. 505,000 elements.
That's too much. And so remember, there's an element limit. There's an element limit of about 100,000 elements.
I have 73,000.
If you're using the student version, that might be too much. But
I think it did.
yeah, you might want to restart ANSYS.
Or should I just wait? Do you think, should you recommend I wait?
If you did 1.1 millimeter, I think you're gonna be waiting all night.
Okay, that's
Closing.
goodbye.
So, yeah. Yeah, so you can assume, so a lot of you are kind of learning is that, the mesh element size, it plays a big impact on the mesh itself. So, if you remember from last Tuesday, generally you want to use a smaller element size. And so a smaller element size would generally lead to a more accurate simulations and it kind of looks nicer too. But everything comes at a cost, right? And so if you pick a size that's too small, it's going to take forever for your mesh to generate. And even if you are able to weight it out, so let's say that you're able to get a mesh with like 1 million elements, and you somehow have a pirated copy of ANSYS that I'm not going to ask questions about. But if you try to run the simulation on that, that's going to take even longer as well. And so there's a delicate balance between how many elements, how much cost are you willing to tolerate versus how much accuracy do you want from the simulation. Okay, so I'll give you guys 1 more minute to get to get the mesh, and then we're going to talk about boundary conditions. All right, good question. So question from the chat in Zoom is that what's the difference between element size under mesh versus element size under body size? Yeah, that's a really good question. So if you specify the element size under mesh, remember that's kind of what we did in activity 1. What this is this sets kind of a global size for your entire product. Under body sizing, this allows you to specify the size for specific areas of your mesh itself. So for right now, because we only have one part, they're both kind of the same thing. But there will be situations later on where you have an assembly of several different parts, and you want to choose the sizing to be different in different parts of the MOS. And so by choosing different or by creating a body sizing object like this lets you specify the size, different sizes in different areas of. So I'm introducing, so for this, for this activity, it doesn't really make a difference because we have one part. But in activity 3, you're actually going to have several different parts of the assembly. And so you're going to need to specify the sizing differently. Is there a question over there too?
Oh, yeah, I was wondering what was the max amount of elements we could have again?
So for the, if you're working on the lab computers, I think the maximum is about 100,000 elements. You'll find out when you run the simulation. So if you try to run the simulation and it's too many, ANSYS will tell you you need to buy the commercial version. If you're using the student version, so the free one that you download on your computer, the limit is 64,000.
I just said 62.
Yeah, so you might get it, but they might have raised them. So it was 64 last year.
I mean, it definitely took 2 minutes.
Okay. So when you go to run the simulation, if it's too many, then ANSYS will give you, will tell you. Okay, so let's go ahead and move on, right? So you're definitely free to kind of keep playing around with the meshing a bit later. It is fun to play around with the meshing. You know, I've done that a lot with my previous projects. But let's go ahead and move on to the boundary conditions. Okay. So remember, boundary conditions is what we talked about last Thursday. Okay. And remember, the boundary conditions, they denote all of the exterior effects that are being applied to our bike. Okay. So for this bike pedal, you know, there are two main effects that I want you guys to account for in the boundary conditions. Okay. So the first effect that I want you guys to account for is the fact that this bike crank is going to be attached to a greater kind of bike. Okay. So I want you guys to assign a boundary condition that kind of encapsulates that. Hate writing with the zoom thing because it makes my writing look like a serial killer. Okay, attached to bike, right? Reading in the mirror of your bath like a scary movie. Okay. Okay. The other boundary condition I want you guys to account for in your simulation is the fact that, you know, there's going to be some load that's going to be applied on this bike crank as well. Okay. And so that load is going to be 100 pounds. Okay, so I'm going to set the value. So 100-pound load. And that load is going to be applied directly on the pedal. So it's going to simulate the situation of someone kind of pressing down on the pedal as they're biking. Okay. So those are the two boundary conditions that I want you guys to specify in this simulation. Okay. And as you're doing that, and this is going to be, again, I'm going to give you guys 10 minutes to work on this. I want you guys to remember kind of two considerations. Okay, the first consideration is that, remember, for any structural simulation, you need to have a fixed support somewhere in the model. So make sure you add that. And the other thing I want you to consider is that, you know, even though I told you that the magnitude of the load is 100 pounds, right? I kind of already told you the location of where it's going to be applied to. It's going to be applied on the pedal, right? But what I want you guys to think about is, I want you guys to think about the direction of the force. And so I'll let you guys kind of think about it and think about kind of what kind of makes sense for the direction of the load. Okay. And so, you know, there's a few things I want you guys to think about as you're doing these things, right? So for the fixed support, right? So we know that there has to be a fixed support somewhere in the model, right? And generally, you know, the location where you apply the fixed support is where your part is attached to something that's bigger than, okay? Because usually when you have something that's attached, when you have this little part here attached to a bigger structure, right? That bigger structure is going to be relatively immovable compared to your part. So wherever this bike crank is attaches to a bigger structure, that's where you want to fix it. Okay. And then for the direction of the load, right? Remember, the goal of this study was to find out, is this bike crank going to be able to withstand the loads? Okay. And so even though I've already given you the magnitude of the loading, I want you guys to think about, what's the worst case scenario, right? So what's the direction that this load can be applied on this bike crank that's going to lead to the highest amount of stress in the bike crank?
into the edge.
Well, so I mean, so the location is already kind of already confirmed, so it's gonna be at the pedal itself. But you can choose to have, the load go, you can choose to have the load go this way, right? You can choose to have the load go this way. You can choose to have it diagonal, right? So I want you guys to choose, the direction of that load vector that's gonna lead to the highest amount of stress. Or to think about it another way, what's the direction of the loading that's going to make it most likely to fail? Okay. So I want you guys to think about that. So let me go ahead and get you started, right? So remember, to add a fixed support, we're gonna right click on static structural here. We're gonna insert a fixed support. Okay. And remember, the fixed support, you're gonna specify the geometry, or you're gonna specify the parts where you're gonna apply the fixed support on. And then the other thing that you're gonna specify here is a force mode. Okay. You're gonna click on force. Okay. And remember, under force, the easiest way to choose a direction is to change this define by setting. So instead of defining it by a vector, you're going to define it by a components instead. And so you're going to individually select the components of the X, Y, and Z directions of them. Okay. And so, to change the direction, you would specify the components differently, but the magnitude of your forcing should still be 100 pounds. Okay. And so if you're going to choose to put it in kind of a diagonal direction, right? So let's say that you're going to do it diagonally in the X and Y direction, right? Then you would use basically, Pythagorean theorem to choose the components. But the magnitude of the loading should not exceed 100. Okay, so I'll let you guys work on that for the next 10 minutes. If you have questions on kind of anything that I mentioned here, just go ahead and ask. But yeah, go ahead and choose the boundary conditions. If you're still working on your mesh, go ahead and raise your hand, and I'll come around and answer your question.
We'll fix that. Oh,
This guy.
yeah.
What's up?
Same thing.
Yeah.
See?
So I agree. So like that's kind of screwed. I'm looking at it.
You see what I mean?
But it's kind of screwed. It's kind of screwed into the bike.
Like, I know that the.
We're gonna go right.
So that's so I would say those holes are going to.
If you want to do it.
And if you want to select multiple circles, you can fold it.
I think if.
But that's probably.
If we make the some.
Yeah, you're right, because that's how what you would use to be transferring like the game, right?
These two, right?
Yeah.
So wouldn't the only fixed part
How'd you get 100?
be this bottom part? So, yeah, it's 100 going.
Actually, no, I think it's not. Figure out the size what's on.
Because we want the decent scale, I'm pretty sure it's this way, so I'm pretty sure these two that's here. These two bits.
Sure.
Like it's the
Yeah, I would say so. Yeah, because basically it's messy for basically you have two screws. So that's whenever you have attachment screws, that's another.
Unfortunately, in this ring.
Yeah, basically anything in that cycle is business. That's what the force is distributed because of the flow is, there's a kind of attachment point that's going to be distributed. So I think it would. Yeah, those all those.
So what it would be, it's like, it's the X direction, just be 100. Yeah. And then there's nothing in the wire.
Unless you want to make it go back and I mean, you could, but I mean, like, but same kind of
Cattling.
Well,
yeah.
Okay, well then,
it changes.
why don't you just not do it? If it's the same thing.
Because it changes depending on the. Changes like that.
Like if you just do like here,
Yeah.
That's 100. I still like doing this 40 fine. I don't think it was. Or if we go. Unsuppressed. Actually, should be. Insert. We don't want deformation for this one, do we?
You do, generally deformation and equivalent stress are the two, you always want those two at least, sometimes you want more than that.
Deformation. And equivalent stress.
You know, I really like one word.
Okay.
That's right. Well, I think we need to put in there. I'm not the. So I put it all.
It's also too. It's my time just this. You didn't choose a solution. You didn't do this. Or barely. Huh. This is not what I expected. So, here. I mean, that was here. Okay. Yeah. So. What about the PSI? Oh, that's what. That's what's straight. Yeah, like speaking your mind, just speak yourself up. So I'm guessing it's just like. Does that make sense? Let's do it, sure. Wait, lower order. What? That's your direction. Here, that's the. I guess it goes out of ways.
I think we're laying them out. You haven't even put it. You haven't. The thing is, but you really need.
No, I asked is for.
No, but put on solution.
Yeah, you have to do.
Then you kind of all.
I just. I think it's. Yeah, because look, I did 50 with a negative 6. Put it all in the negative.
That's not like,
You read bikes, so I'm reading. I don't know if bikes work. Yeah, I've written the one.
but I'm really sick of phonics.
Refinement's more provided.
I now have more than 2 for sources. I've got it 40. Yes, that's where it's 40 plus.
Oh, you did give more than.
Okay, so let's, so once you've kind of decided those on the fixed supports and the forwards, so let's go ahead and run the simulation. Okay, so actually, let me get rid of my serial killer writing here.
No, for the.
Okay, so walking around, I think everyone's kind of figured out where the fixed support should go. So the fixed support, you should apply on this side of the model, right? So generally, what my kind of thought process is that, wherever this part attaches to, normally there's going to be some screw holes or there's going to be some screws. So that's usually where I like to fix the model, right? And so in this case, for a pipe, the 2 screw holes are these ones right here. So I would fix it here. Some of you have also fixed this center part right here. That's fine for this case. It's not gonna make a big difference in the result. But you know, because these two smaller holes that, you know, those are the ones which are gonna be screwed into the bike frame, that's where I would fix it. The force, of course, is being applied on the other side, which is where the pedal is. Okay. Now, the big question is, you know, what direction do you want to put the force in? And kind of what I told you is that you want to choose the direction that's going to result in the most likely failure. Okay. And so, you know, there's questions of, you know, should you put it in the Y direction, in the Z direction, in the X direction? Well, you know, what we have here is we kind of have a part that is essentially like a cantilever beam, right? So we have kind of a long slender part. It's fixed on one end and we're applying a force right at the end. And so in these situations, when you have kind of a long slender part, kind of the easiest way to kind of break it or snap it is to apply a bending force, right? And so if you look, if you have a pencil in front of you, right? And so if someone told you to snap it, right? The most, you know, the most intuitive thing that you would do is you kind of apply a bending load, right? And then you would kind of try to snap it like that. You wouldn't try to compress it, or you wouldn't try to, you know, bend it in kind of a weird angle. You try to snap it with a perpendicular force. Okay. And so for that reason, you know, I've chosen to apply my force in the Y direction. Okay. Z direction would work pretty well too. The only thing with the Z direction is that, you know, it's not often you're going to apply a force in the Z direction on a bike, because, you know, a Z direction would be something that's coming out of the cage, and that's usually not a direction that a person would press down on the pedal. So Y direction, Z direction, you're probably going to get the maximum force there, but Y direction is probably a bit more unlikely in terms of what someone's actually going to use the bike. Okay, so let's look at the stresses. Okay, so when I plotted my equivalent stress field, it looks like this. I get a maximum stress of about 13,000 psi. If you want to change the units, I'm using US customary with inches right here. And I get a total deformation of about 0.05 inches. Okay, so that's with a 100-pound force on the bike. So now, of course, the question is, you know, with this 100-pound force, is the bike frame going to fail? Let me come back to the project specifications. Okay. Okay. So under problem 5 right here, you should see that this material has a yield strength of 35,000 psi. So as long as the equivalent stress is less than 35,000 psi, then the bike crank is not going to fail. It's going to be completely fine. Okay. So let's come back to our simulation. Okay. And we see that the maximum equivalent stress is only 13,000, right? And so since 13,000, I guess it's 13,300 is less than 35,000. 35,000 being the yield strength of this material. And in this case, this bike crank will survive. So you can apply a 100-pound force on this bike crank and it's going to be just fine. So that answered that question. So that is the main part of this activity. Okay, so for homework, so let me go over kind of what you guys need to do for homework for this activity here. So we've basically done problems 1 through 4 already in the class today, and so you guys are going to pick it up from problem 5. And so in problem 5, what I want you guys to determine is the maximum load or the maximum amount of force that this bike crank can take before it actually becomes in danger of breaking. Okay. Okay, so for this part, what you're going to do is you're going to come back to your simulation, you're going to come to your force here, and you're going to increase this force magnitude until you see a stress that's strong enough to break. Okay. And so we already know that 100 pounds is not strong enough to break this bike crank. So let me go ahead and increase this to 120. Okay. So you increase the load amount to 120, you click solve. What you should see is that the equivalent stress is going to go up. Okay, so you can see here that I've increased the load to 120, so you can see the equivalent stress has gone up to 16,000. Okay, so I want you guys to kind of run the simulation a few times. So I want you guys to change the mode, run the simulation, check the stress, change the mode, run the simulation, check the stress, and I want you guys to get as close to the yield strength as possible. Okay,
How do we know when we reach?
So the yield strength in this case is 35,000. But I want you guys to work with the factor of safety of 2, okay? And so instead of getting 35,000, what I want you guys to get up to is, I want you guys to get as close to 35,000 divided by 2. That is 17,500. So basically, I want you guys to run the simulation over and over again, changing the amount of load until you get a maximum stress that's as close to 17,500 as possible. Okay. Okay, so right now you can already see that 120 is not enough to get up there. Okay. So we need to increase this a bit more. So I'll increase it one more time because I already know the answer in my head. So if I get any closer, then we'll know the answer. But let me go up to 122.2. Okay. So if I increase the load to 122.2, you can see that this equivalent stress creeped up a little bit more. So it went up from 16,000 to about 16,300. Okay. So I want you guys to kind of iterate on this, change the loading, get as close to 17,500 as possible. Okay. Okay, so that's problem 5. Problem 6, I want you guys to do the same thing. I forget to fix this every single year, but problem 6, I want you guys to do the same thing. I want you guys to increase the load until you reach 17,500, but I want you guys to change the direction of the loading. So instead of applying a bending force, for problem 6, I want you guys to apply a force in the compressive direction, okay? So instead of applying the load in the Y direction, I want you guys to apply the load in the X direction, okay? And then I want you guys to do the exact same thing. I want you guys to increase the load until you reach a maximum equivalent stress of about 17,500. Okay. And what you're going to see is that, because the direction of the load is changing, we're instead doing a compressive stress instead of a bending stress. And so what you're going to see is that this bike crank can sustain a lot more load in compression than in bending. Okay. So you can see here, I actually did tensile stress on accident. But you can see here that the stress is much lower in this case. Okay. So that's problem 6. So problem 6, I want you guys to find the maximum load that it can take in compression. Okay, so from there are a couple other parts. I'll fix the numbering. I'll go back and change it. So problem 7 is going to be summarizing your findings. Okay. So from this activity onwards, this is going to be a part of every single activity. I want you guys to get in the practice of communicating your finite element results to other people. Okay. On the one hand, it's great to be able to write kind of a full technical report with lots of figures and detailed information about your mesh. But in reality, when you're working with finite elements and you're communicating things to like your manager or your coworkers, a lot of times they're not going to have time to read a whole report. So I want you guys to get in the practice of communicating your finite element results and basically like an email. And so in this email, you need to communicate a few different things. You need to communicate, first of all, your results, right? And so you can think about the objective of your finite element analysis and whether your objective was met, okay? And so in this case, our objective was to find out whether this bike crank would fail under a 100-pound load. Okay, so you need to express that in your summary. Another thing that you need to communicate is you need to communicate that, you set up your simulation properly, okay? So you need to have some information on the mesh that you created. You need to include some information on the boundary conditions that you specified, a little justification on the mesh size, a little justification on the boundary condition that you chose. Okay. Because you need to be able to convince people that you set up the simulation properly. Okay. And then just some essential information about the results. So the maximum allowable load, the stress, and a recommendation on whether the bike crank should be redesigned. Okay. And ideally, this should fit within, less than a page. And so maybe about 3/4 of a page. And so I always tell people in your summary, you should include at least one figure. So one figure is good. And so you have to think about kind of what's the figure that kind of makes the most sense. What's the one figure that kind of encapsulates everything about this activity, include that, as well as kind of a quick summary of kind of everything that you did. Okay. All right, any questions on this part right here? All right, and then finally, so problem 8, I'll fix the numbering, is I want you guys to run through another finite element analysis on a bike frame. Okay. And so if you go back to the page on Canvas, you'll see that I posted a second CAD model, right? And so it's called Cycle Chop Ram 1, right? So this is a CAD model of an actual bike frame. Okay, so you can look at the frame right here. And I want you guys to do an analysis from scratch on this frame, okay? So I've included instructions on, the limitations for the mesh. I've included some instructions on the loadings that you need to apply, okay? And so I want you guys to kind of do those things and answer some questions on that simulation. Okay, because, now that we've kind of covered all the basics of ANSYS, now it's kind of getting practice and doing it in different situations, okay? So we spent the majority of today working on the bike crank itself, but for this activity, I want you guys to do another analysis on this frame as well. All right, any questions on the activity here? Okay. All right, so that's all I got planned for today. So there's about 10 more minutes. And so if you have any questions about the activities or anything else you want me to look at, I'll walk around. You have the rest of the time today to start working on the different parts of the activity. Or if you just want to go home, you can. So thank you guys for coming today. I hope you guys enjoy our second activity. I'll be making the rounds a bit after this. And I'll see you guys all on Thursday. I'll come back.
Yeah, so.
Oh, no, this is the ANSYS. It's over.
Oh, yes.
Where did you use that for? Oh, right. Also, if you ever need a pen, here you go. Right. That's it. It's just that one. Oh, here's that. I mean.
You push, you kind of put it on. For the B direction. That was not.
It's too.
I may come back.
I need the presence number. This one?
Yeah.
I don't think it's straight.
Maybe it's the mesh size, maybe it turns on. Yeah, it's yes, this seems not.
Wait, let me save it. So, active is depend on the rating. Either. We want to shoot it at the right.
Huh? Your elements are too small.
So the Y direction. You're welcome. And X direction meaning it's 6.
No, it's too late.
What is on the little between?
What's up?
I just need to say this. My head can hear
See you guys.
Wait, so when they come back, it's going to open.
It's not a factor safety.
Yeah.
This is more just because I found it.
And it can survive 3,000 pounds of force.
No.
Hey,
This
yeah, I mean, getting it right on the nose, but that was 500. I want you to say. That's it, right there.
So I wouldn't get fired on my job.
Probably. Most likely.
Most likely.
I live in fear every day, but I'm not going to use this district.
It keeps you on your toes.
Yeah, well, certain powerful people don't. There's one.
The PE.
Oh, yeah.
No.
What?
We got your back, Mrs.
Thank you, guys.
Right. We're back with Teamsters like they did.
Well, strikes don't work here.
If they fire you, we'll protest.
Thank you, guys.
I got a raise of $1. You also got a raise.
Excuse me.
Matter of habit, bro.
So we also got.
That's true, yeah, no, that's a good consideration. So, yeah, so that 100-pound force, remember, when you're pushing down, right? So a lot of your weight is being, but when you're pushing down, not only is it weak, but you're also pushing down with like body. So it's kind of disproportionate kind of to your.
Oh, you joined. Are you gonna do that side?
Yeah, so the 100 pounds was kind of like an approximation, so it's, even if you split between two days, it's not like a 200 pound. So it's not like maybe.
Like, there's not a way to get it
so kind of bring extra force or actually muscle.
But you technically could, I think you could.
I would kind of consider that question there was kind of more of a qualitative question, so. It's, of course, it's really less you got a deep understanding of biomechanics and how much tension that's can exert. It's kind of hard to get exact numbers on that. But just kind of take it as if 100 pounds is kind of
Did that to me yesterday.
That answer your question, Ben?
I was like, that is a very good question. We'll ask you later on. Why? That's pretty good. Yeah.
Look,
I've only said something.
It's true, yeah.
Oh, why? That's why.
So this mesh thing, everyone should do it roughly in the same place. Unless someone's very good. So these results converge. So whether you have like a 70,000 element mesh or a 10,000 element mesh, I think the results are wondering. I think the only difference was if someone had like a 200 element mesh, then that would increase.
I think this is.
But for most people, I think people are going to be the same ball.
Doing 130.
What's up? Oh, yes, you're gonna close, You're gonna close, go, okay, go ahead and click save.
We're doing fine.
So I'm just doing it. And that WPZ, that's the one you're going. And then you're working on this, home, you just double click that. Yep.
Why not? It's the best class.
You're saying that you don't have anything.
How was the exams like?
It's gonna be. He talks about conditions, not within the question by conditions. So yeah, so you have like this. Typical steel being that also. Wall steel.